Amdahl's law. Amdahl's law states that if you improve the execution time of a fraction f of a computation by a speedup p, the overall speedup is 1 over 1 minus f plus f over p. So if you look at in here, this is an illustration. What Amdahl's law states is that you're improving this part, you're improving the execution time of this part. Okay, so it's get divided by 3, for instance, if p is 3. F here is 75%, but that part is going to remain constant. Same here and same here. So your speedup will be intrinsically limited by the part that is not accelerated, that is not improved by putting more parallel resources in it. So if we look at what it gives, if I'm assuming the portion of the code I have is only 50%, so I can improve only 50% of the code, my speedup is going to be bounded by 2. I cannot get more than 2 as a speedup. And this is obvious since I'm only reducing the time for only half of the execution time of the code. Here is a curve for 60%, 70%, 80%, and here is 98%. Now you can see something, and this is the ideal speedup. So as you see, if you want to get efficiency from a large number of parallel elements, you need to have a very large fraction of your code that is parallelized. Okay. This law was actually designed by Amdahl to show that there is a big issue with parallel computing. If we look at the impact of this law on what we have to do on parallelization, if f is small, okay, let's say less than 50%, the benefit from parallelization and optimization is going to be very small. Okay. And it also gives you a theoretical upper bound. Let's assume that p equals infinite. Okay. In that case, that means the part that is accelerated, the execution time of this part, is 0. So your speedup is bounded by that. This is what we saw on previous curve. The Amdahl's law doesn't tell everything. For instance, Amdahl's law doesn't take into account overhead of managing parallelism. Okay, so it considers that f over p, the execution time for the parallel part doesn't change as p increases, but in practice you have some overhead to manage parallelism, so this is not taken into account. So Amdahl's law is really stating an upper limits. And when you have a fixed size problem, you will have some work starvation. So anyway, at some point you have too many processors for what you have to do. So Amdahl's law is not taking that into account either. So here are the questions. Amdahl's law, is it giving a maximum or a minimum for the speedup values? Is f a static or a dynamic value? That is a portion of the time spent in the parallel part. When we consider serial versus improved constant ratios, that is this ratio, do you think this is a reasonable assumption? And if not, why? And when you consider Amdahl's law, is it a good idea to have a large number of slow processors? The idea behind having slow processors is they will use very little energy, but you want a lot of them to get some computing power. Here are the reference, the original paper from Amdahl, and this is a paper considering the Amdahl's law in the multi-core era. And see you in class.